This is the second in a series of levers, pulleys, inclined planes, torque, and angular momentum. In this section, we'll talk about levers. We generally talk and classify levers in three different classes, but I don't think that's critically important. But the difference is that there is something called a fulcrum, and that's the point at which we pivot everything. Keep that in mind. The fulcrum is the pivot point. That's the point that things move about. So let's assume we have this lever at this point. In what is called a class 1 lever, again, I don't think calling them class 1, 2, and 3 is critically important, but regardless, you're pulling up on this end or pushing down on this end, and this end goes up or down. In what is called a class 2 lever, this would be your main force, F1, where we had F1 here and F2 here. And F2 would be something here. And then in the third type of lever, so this will be number 2, and the third type of lever, you have the fulcrum here, and you're pulling up here with your force F1, and you're lifting a weight here, we'll call F2. Again, it's not critically important to talk about the difference between these. What is critically important is that the fulcrum is the pivot point. Everything is going to be measured from that pivot point. That's going to be your basis of all measurements. If you'll keep that in mind, then you can easily work lever problems, which is why we generally teach them in middle school. And this little session is just a catch-up if you forgot or need a refresher. So how do we work lever problems? Let's look at it. We put a force in on this end, which we will call F1. That pushes up on this end with a force F2. We might have a rock here, or we might have a person here, like a seesaw. Everything is measured from where the fulcrum touches right here. So this will be called distance 1. What is distance 1? It's the distance between force 1 and what? The fulcrum. This we will mark as F2 because we are D2 because we call this force 2. How do we measure distance D2? From the force F2 to what? The fulcrum. So everything is measured as a distance from the fulcrum. And the lever equation works more like this way. You multiply that distance times the force, and it's equal to this distance times this force. Now actually, we call the force times distance. This would be work if the distance were in the same direction as the force, but it's not. The distance is in this direction, the force is this way. So we could, if we talked about this distance, we would have force times distance and have work. But in this case, we have a lever arm pulling out here, a force this way at right angles to it. We call this distance times the perpendicular force here. That force times distance, we call that the torque. Let's call it T. That torque has to be equal to this torque. So this was F1, torque 2 is F2 times D2. Those two torques have to be equal to each other to keep this in equilibrium. And that is all there is to lever problems. Well, let's look at a class 2 lever. Here we're pulling up with a force F1. And let's say we have a weight hanging down here, which would be force F2. How do we work this problem? We get the distance, what, between F1 and F2? No, we get the distance between F1 and the fulcrum, the pivot point. And so that becomes D1, F1 times D1, and that becomes the torque that F1 produces. So the torque that force 1 produces is force 1 times that distance 1. How about force 2? Here is the force. How do we measure its distance? Between it and force 1? No, between it and the pivot point. So this becomes D2. And we have torque 2 is equal to F2 times D2. The torques are equal to each other because we're in equilibrium, so we have F1 times D1 is equal to F2 times D2. Same thing we had up here. F1 times D1 is equal to F2 times D2. But remember, the distance is always defined as between the force and the pivot point or the fulcrum. If we look at a class 3 type lever, then you're pulling up here with a force F1. And let's say lifting a load here, which has a force F2. Now what distance do we measure? Well, this is D1. And that's torque 1 because it's this distance times that angle. Now what about F2? What is this distance? Always to the fulcrum. So this is F2 times D2. And that's torque 2. We equate these to each other and the formula looks the same. F1 times D1 is equal to F2 times D2. Students never get this mixed up. They always remember this equation. But they forever mix up what it is they're doing and forget that you're measuring all the distances from the force to what? To the fulcrum. Here's a problem. Suppose we have a 10-foot lever. How much can a 500 Newton girl lift if she places the fulcrum 1.7 feet from one end? Well, think. Obviously, if the total lever is 10 feet long and she places it 1.7 feet from each end, then the other end must be 8.3 feet. So if we look at what she's done, she has the fulcrum placed 1.7 feet, and then she will push here with a distance of 8.3 feet. How much can she force it? Well, if she only weighs 500 newtons, then that has to be the force. So let's say she pushes or sits right here on this end. She can only push down with 500 newtons. Now how do we work it? Well, we know that torque 1 is equal to torque 2. And what is the torque? It's the force, the perpendicular force times the distance, and that's equal to the perpendicular force of number 2 times the distance. So I am trying to solve here and find out what force 2 would be. So if I solve this equation for force 2, I get force 2 is equal to the force 1 times D1 over D2. Force 1 is 500 newtons. D1 is the distance between force 1 and what? The fulcrum. So that is 8.3 feet. D2 is 1.7 feet. And you say, well, don't I have to get that in meters? Well, no, because the feet cancel out, and I'm left with an answer of F2 just being in newtons. And I get 2,440 newtons. Now let's work a problem with several different weights. Suppose we have a 10-meter pole. And let's place the fulcrum directly in the center. And then let's put a weight on this end of 100 newtons. And on top we'll mark the distance of the pole. So this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 along the pole. And so let's place a weight here of 300 newtons. This will be at 7, as measured from here being a 0, just counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because the pole is going to be 10 meters long. And let's place a weight here of 400 newtons. And then let's ask the question, where would we have to place a weight on this side of 500 newtons in order to exactly balance this out and be at equilibrium. The assumption is that the bar here has no weight at all and does not contribute to it. So let's go over the problem again. We have a 10-foot bar, which we can ignore its weight. The fulcrum is in the center at 5 meters from one end. We have 100 newtons at one end. We have 300 newtons at the 7 meter position, and we have 400 newtons at the 10 meter position. And we want to know, we have a 500 newtons we would like to hang on here, 500 newton weight, and we would like to know where do we hang it so that this is in equilibrium. Well, we know that the torques on, let's say, the right hand side are going to pull it around this way, so the torques clockwise would have to equal the torques counterclockwise. So if you think of this as a pivot point where the fulcrum place is right here, then these weights will tend to swing the bar around this way. These weights will tend to make it go that way. In order to be at equilibrium, the torques have to be equal to each other. So the counterclockwise has to equal the clockwise. So let's see what the counterclockwise torques are. That's the torques on this side. Well, everything is going to be the force, we'll call it I, times the distance I. That's how I'm going to calculate all the torques. So let's look at the first torque, the 300 newtons. It's 300 newtons. How do I measure its distance? Its distance is, of course, measured from the force to the fulcrum. So that's at 7, it's going to 5, so that is 2 meters, the distance between that force and the fulcrum. Now, another one going clockwise is the 400 Newton force. Now, what is its lever arm here, as we call it? Well, if the fulcrum is at 5 and the pole is 10, 10 minus 5 must be 5 meters. So now I have two torques, this torque and this torque. This one pulling this way and that one pulling that way. And that has to equal the torque in the other direction, which is 100 newtons times its lever arm, which is 5 meters, because we always measure everything to the fulcrum. But the problem says we want to place 500 newtons in here and have it balance out. So in order for this to be equal, I now have a torque of 500 newtons, but I do not know where it needs to be. X will tell me how far it needs to be from the fulcrum. How do I know that it's on this side? Because I set it up that way. It has to be on this side to balance that out. So now I solve for X. X is going to be 300 newtons times 2 meters plus 400 newtons times 5 meters minus 100 newtons times 5 meters. All of that divided by 500 newtons. Well, the newtons are all going to cancel out, and I will be left with units of meters, which is correct because that's going to be my distance X. And when I divide this, I get 4.2 meters. So this says that if I want to balance out this pole, I need to place at a distance of 4.2 meters on this side from the fulcrum. So that would be 1, 2, 3, 4.2, somewhere in here, because the whole thing is 5, a weight of 500 newtons. So that's where it needs to be, at a distance of 4.2 meters from the fulcrum, or 8/10 of a meter from the end that we started measuring with. Because if we started here at 0, and that's 4.2 from the fulcrum, we're only left with 8/10 of a meter. Let's consider this problem where I have a fulcrum here, I have a 10 meter lever, I have 300 newtons pulling up at the end of the 10 meter point measured from the fulcrum, I have 200 newtons at the 2 meter point, I have 100 newtons at the 4 meter point, and let's say that I want to add 350 newtons somewhere in here, it would pull down, and I want this to be in equilibrium. To be in equilibrium, the torques in the clockwise direction would have to equal the torques in the counterclockwise direction. So there are going to be 3 torques in the clockwise direction. 3 things that are making this turn in the clockwise direction. It'll be the 200 newtons, the 100 newtons, and my 350 newtons. So let's put that equation together. The torques in the clockwise direction becomes 200 newtons times 2 meters plus 100 newtons times 4 meters plus 350 newtons times, I don't know how many meters, x, but that has to equal the torque in the opposite direction. Well, the only one turning it this way in a counterclockwise direction is the 300 newtons times 10 meters. Now I solve this for x, and when I do, I have x is equal to 300 newtons times 10 meters minus 200 newtons times 2 meters minus 100 newtons times 4 meters divided by 350 newtons. All the newtons will cancel out, and we're left with meters. And when we solve this for x, we get x rounded off to 2 significant figures as being 6.3 meters. So we would have to place a 350 newton weight at a distance of something like 6.3 meters, always measured from the fulcrum, of course. Place it right here, and that would equal the torques, so that this lever arm would be in equilibrium. The 3 forces pulling it in the clockwise direction would equal the 1 force in the counterclockwise direction. And so we would place the 350 newtons at a distance of 6.3 meters from the fulcrum.